Hi everyone, welcome back. So in this lecture, I will continue to talk about fundamental equations for the thin airfoil solutions. So we have this equation right over there. All we need to do is we want to solve the gamma x. This is the integral equations, and the left-hand side is the integration of the unknown function with a known function x naught minus x. The unknown function is gamma x. On the right-hand side, we have the magnitude of the velocity, u infinity, with a vector sign, and we kind of compute the norm of the free stream velocity. The second term is, on the right-hand side, is the angle of attack. The third term is the slope of the camber line evaluated as x naught. And this equation has to hold at any point between 0 and c. Okay, between any point of x naught between 0 and c. So now we will solve the gamma x. Before we first solve gamma x, we will first conduct change of variables. So we will not really solve gamma in terms of the x, but we will solve gamma in terms of another variable, which has one-to-one correspondence with x, which is theta here. So the theta, if you look at the expression here, if I change theta from 0 to pi, I basically change x from 0 to c, right? Because cosine 0 is 1, so 1 minus 1 is 0. So x is real. X starts from 0. If theta is pi, cosine pi is minus 1. So 1 minus minus 1 is 2. So 1 over 2, c times 2 is c. So when theta equals to pi, x equals to c. The reason why we're doing this, because you will soon see in a few minutes that there's a huge benefit. You can actually have a very nice solutions by just performing these transformations. Also, note that we also have a x naught, right? We have an x naught before. So x naught correspondingly, it will transform to x theta naught. It will be a corresponding theta naught. Okay. So now what I'm going to do is, remember the left-hand side is the integration with respect to x. Now I will change it into an integration of theta, which means integration lower limit and upper limit will change from 0 to c to 0 to pi. And we will sort of rewrite this equation as gamma as a function of theta, and dx will also be written as some sort of function of theta. Okay. So here's this is what's going to happen. So let's first note that if you take the dx over d theta, what you should get is dx equals to 1 over 2c. The only thing inside here is cosine theta. So cosine theta is the derivative is minus sine theta. So we have two negative sign. We have end up with a sine theta and d theta. Okay. So which is basically this expression here, the dx equals to half of c times sine theta d theta. Then we can rewrite the equation as the following one, as this one. Okay, basically what happened is you just need to notice that the x naught is this 1 over 2c times 1 minus cosine theta naught. And the x is you sort of corresponding has a relation with cosine. So if you just use let's say you just you use the lower equation, let's say equation 1, equation 2. If you compute equation 1 minus equation 2, you can imagine that the only thing left is the cosine theta and minus cosine theta naught, right? So basically this is what happened here at the denominator. And then you have some factor, you can sort of cancel them out. And also considering the dx expression over there, this expression is basically what you get. Trust me, it's a very simple algebra. You can verify by yourself. Okay, so this equation is solving the gamma distribution, but in terms of theta. The theta is from 0 to pi. If you can solve gamma theta, you can get the gamma theta by just using the change of variables. Okay, so it's very easy. Okay, so now let's say I'm going to solve this equation right here. So first notice that I have a subscript theta naught. Basically that means is just gonna solve. Just basically what it means is, when I compute the slope will be evaluated at x naught, which is corresponding to theta naught. Okay, good. So one important thing I want to talk about is this equation. Let's say equation star. This equation star has the following general form of solution for gamma theta. Okay, so let's look at this form of the solution. This form of solution says that gamma theta will be looks like it will be a sine cosine trigonometric series, okay, and with unknown coefficient a0 to a n, probably a infinity. It's infinite number of actually these numbers are real numbers, a naught to a n real numbers, unknown real numbers, and they actually determine the gamma theta. So this is actually sort of a general form for the solution, as why this is the general solution for the equation star is beyond the scope of this course. Okay, so please accept this. And now, in order to find gamma theta, the only thing we need to find is a naught to a n. If we can find a0 to a n, we basically figure out the gamma theta. Okay, so now what we should do is we will plug in this equation for the gamma theta, plugging back here. We get a sort of a messy equation, kind of a pretty chunk of messy equation, and let's see what we will get. The first thing another thing I want to notice is the gamma pi is actually 0. So the remember the quota condition, we need gamma c equals to 0. So in the theta space, that will be gamma pi equals to 0. And actually gamma pi equals to 0 is actually built in. So if you look at the second term over there, of course, sine n pi is going to be 0 always. The first term is not too obvious, but if you use L'Hospital rule, you can figure out that if you can figure out the limit, because it's limited right now. If you put theta equals to pi, it's a 0 over 0, so you can't really tell. So let's use L'Hospital rule, which is going to be minus sine theta divided by cosine theta, and theta equals to pi. So obviously you should get 0, right? It's basically 0. That means the gamma pi is 0. Okay. So now if we plug this in, remember that if we plug it in, we have two parts. The first part is correspond to a naught. The second part corresponds to a n, with n larger or equal to 1. So similarly, the left-hand side, we will have two terms. This is the first term, this is the second term. Okay, so there are actually something nice we can show. We can actually show something about the 1 over pi times this chunky integration is actually 1. Okay, when you integrate over theta, no matter what theta naught is always 1. For the second part, the 1 over pi times these chunky integrations over here will be a minus cosine and theta naught. These are very interesting identities, and I have posted proofs for those identities, which require several pages to prove. I also uploaded on LMS. If you are interested, you can take a look. Okay, so once you use these two expressions over there, these are the derived identities, and you plug them back to here, you will end up with a very nice expression. This is beautiful. This expression basically tells you, let me first remove, remove the geometry information to the left and move everything on the left-hand side to the right. So basically you end up with this equation. This equation basically tells you, okay, this equation basically tells you, so if you look at the left-hand side should be a function of theta naught, right? Because it's evaluated at theta naught. And theta naught is varying from 0 to pi. Okay. On the right-hand side, alpha is sort of fixed, given. A naught is an unknown but fixed number, and the a1 to an and to a infinity is also an unknown number, but we have a cosine n times n theta naught. So if you look at this expression here, if you want to find out a0 to an, that's basically what you're doing is a trigonometric expansions. To find those trigonometric expansions, the trick we use is the trick we're going to use is we will use the orthogonality of the trigonometric expansions, which is let me see. I think I have written down the orthogonality of cosine series in the handwritten note in IMS. Please check them out. So basically, at the end of the day, what you're gonna get is the alpha minus a naught is basically related to just the integration of the slope itself. Okay, just the slope of the camber line itself, and the an for n larger than 1, larger or equals to 1, that's basically comes from an integration between the slope profile and the sort of the cosine signals. And the cosine signals depends on how large the n is. The larger the n, that means the larger frequency it is. Okay, means it will oscillate really fast. Okay, so this equation basically tells you you can just do a numerical integration to get the a0 to a naught coefficient from the geometric profile of camber line. Once you get what is a naught and an to an, these thing are the thing determines gamma x because of this beyond the course general form, right? It basically tells you if you know a0 to an, you basically figure out the gamma theta. With the gamma theta, because you know the x and theta relation, you figure out the gamma x. Okay, good. So this is actually a summary slide about the solution to vortex strength density gamma of sort of a cambered thin airfoil. So the cambered basically meaning that the DC sort of the slope of the camber line is not zero. But if it's zero, it's also included in this form. So, but it's a fancy just a kind of a way to say it includes the effects of a zero, sort of non-zero camber slope. That means it's a cambered thin airfoil solution to the cambered thin airfoil. So it's something like that. It's a basically we have a this is basically our camber line, and it's a very thin airfoil, and the potential flow solution around this can be expressed. It can be solved just by using the equation in this block. Okay. So you see the profile of the geometry profile comes in here, and you just need to compute the integrations. You get a naught to an, then you will get gamma theta, and when you get gamma theta, remember gamma theta basically tells you phi a, right? So phi a plus phi infinity is the phi for the entire potential flow. Okay, good. So the overall logic is you have the geometry information, you compute aj using numerical integration, and then aj tells you the gamma theta thanks to the beyond the course general form, and then you use the theta x relation, you can figure out the gamma x. Figure out the gamma x, you can figure out the aerodynamics of the airfoil. Okay, so the reason why is because if the gamma x is known, we basically know the vorticity distribution along the thin airfoil. By using Kutajuk-Volsky's theorem, we can actually compute the lift, and we can actually do a lot more, many other things as well. Okay, so let's first apply this to a simple case. which is a symmetric airfoil case. So symmetric airfoil basically implies that the slope of the camber line will be 0 everywhere. Okay, if this is 0 everywhere, then I think A0 and A naught, so it's A0, for the A0, that's going to be alpha. They only come from the first term contribution. Other terms are going to be 0. Okay, that means the A naught is going to be alpha, and an will be 0 for any n larger or equal to 1. Okay, so then the gamma theta will have a much simple expression. So the gamma theta is basically come from, you just plug in A0 equals to alpha and an equals to 0 to this expression, you will get the gamma theta, which is this expression right over here. Okay, so as you can see, an interesting thing is that you can actually right now just convert them back to gamma x by using this following transformation. Remember that x is 1 over 2c cosine theta, 1 minus cosine theta, sorry. So you can actually have this expression, you can derive cosine theta as a function of the x, okay? So then by using cosine, the identity of cosine theta squared plus sine theta squared is 1, we can actually back out the sine theta as a function of x. And then we just plug in the equation right here, we basically get a gamma as a function of x, and we get the expression, looks like this, and after a little bit arrangement, it's something like this. Okay, if you look at this equation, you will see that when x equals to 0, there is a singularity over there. Okay, so basically when x equals to 0, there's a singularity. That means that the reason why it happens is because if there's symmetrical airfoil over here and there's an angle of attack, so the stationary point is probably going to be here, and the flow would have to travel upstream and turn around a extremely sharp leading edge. This sharp leading edge has 0 curvature, radius of curvature. So the fluid has to turn really, really fast. If it has to turn really, really fast, there should be some sort of infinity suction over there, which corresponds to the sort of infinity vorticity over there, point vortex over there. That's basically corresponds to the singularities of this point here. So when x approaches 0, the gamma x will be it goes to infinity. Okay, so this result is not unphysical. It actually has a physical interpretations. Okay, because the fluid has to turn around really, really fast around this sharp leading edge. Okay, so of course I have just said right here the flow has to turn around an infinite sharp leading edge. Okay, so what's the force on this thin airfoil? So on this thin airfoil, there's only going to be pressure because it's a potential flow solution, so there will be no shear stress, only pressure. And since it's only pressure and it's actually a thin airfoil, everything actually can be simplified a lot. Because remember that we also assume sort of this sort of small camber, small camber slope, and small angle of attack. So with all those things, if you add them together, you can actually convince yourself that all the forces over there is just pressure, lower pressure minus upper pressure, and integrated over the entire chord length, and the force should be pointed, on the normal direction respect to the chord length. Okay, so if we use the Bernoulli equation, we can end up with this relation. Basically, it tells us the relation between the upper pressure, lower pressure, upper connecting energy, lower connecting energy. Okay, so the delta pressure can be written as the difference between the connecting energy. So if you use the sort of the mass conservation in this plot, you can actually show that the normal component W in the lower and upper surface will be the same, thanks to the mass conservation. And so if you compute the pressure difference, there's a pressure difference which is only come from the streamwise component, U component. And I think I've derived a similar expression in the last lecture in person. So you can see we can just expand these connecting energy difference out as the sum between them and the difference between them. And then you can see you can just, the first term basically goes to 2, I think it's 2 times rho infinity times cosine alpha because there's an angle of attack. And the second term, the difference actually becomes the gamma x. So basically it tells you that the pressure difference is just rho u infinity times the gamma x. The gamma x is kind of a differential Kutajuk-Wolski lift theorem, right? But in a differential sense. Okay, good. So once you have this, still remember we're applying this to symmetric airfoil, we can compute the sectional lift force. The way we're going to compute this is we're just going to plug in the gamma x relation because what we derive here is that we know the pressure difference is coming from the gamma x. We know the gamma x as a function from here, right? This is our expression for the gamma x as a function of x. Then we just plug in here. Everything else is known, so let's just integrate this thing. Again, everything about those integrations is actually easier if you do it in the theta space. So again, I converted it back to theta space, and it might be a little bit messy here, but trust me, this is all correct. You know the relation between x and theta, and you know the gamma theta expression, just plug in right here. And then you perform the integration in this. Then first, of course, sine theta cancels out, 2 cancels out over there. And then you put the u infinity in the front and put c in the front. So you get this expression right here. And then you're going to integrate in 0 to pi for 1 plus cosine theta d theta. And the second term will cancel out, so that only the first term left. So it's going to be just a pi over there. So now, let's say if we compute the non-dimensional lift, basically the lift coefficient, now we just only need to do is L prime divides by the kinetic energy times the coordinate c. So we get a very interesting and nice expression, which is the CL, the lift coefficient, is 2 pi alpha for symmetrical airfoil. That means, the alpha, by the way, is in radians. That means if I increase sort of 1 radian in my angle of attack, the lift coefficient will be increased by around 6.28, right? It's basically 2 pi. So this is actually a very nice relation, and it's actually a kind of the iconic theory in aerodynamics. You cannot find it in any other class like fluid mechanics, turbulence. You won't. And this is the most beautiful result in aerodynamics class. Okay, the slope basically tells you if you plot the lift coefficient plot, the slope will be 2 pi when it's near the angle, near a sort of a small angle of attack. Okay. So now let's just like when we're doing homework, how about let's just compute this let's just compute the pitching moment. So let's